Hello, I am Rosemary Alden and I am presenting my undergraduate research poster, Trade-offs in Forecasting of Residential Electric Loads with Data from Smart Meters and Intelligent Circuit Breakers. This research was supported in part by an NSF grant on human behavior, smart homes, and grids. A special thanks to my advisor, Dr. Chris Ababe from Marquette University, and my main academic advisor, Professor Dan M. Iannell at the University of Kentucky. For machine learning projects, it has been found that most of the time spent on the project is spent on pre-processing data. This lengthy portion of the project includes formatting data to be usable in models with correct timestamps, then selecting, isolating, or calculating measurements of interest, as well as removing or estimating missing data points, and doing conversion to desired units. Visualization of the data is then required to ensure logical and correct basis for understanding predictions. Time spent on pre-processing is directly affected by the form data is downloaded in and the amount of data included. For instance, the detail provided in documentation may or may not fully explain the measurements included. Therefore, assumptions and clarifications will need to be made for big data projects. Data pre-processing for this project was completed in R and Python. The assumptions were that missing data points were filled with averages of the previous and following measurement. There are multiple public databases available for residential load forecasting. They include data collected from smart meters, plugs, current transformers, and other sensors. Acquiring high-resolution data from residencies, including published appliance types and building specifications, is crucial to transition residential electric load forecasting to be more widely used by utilities. The additional information allows for analysis of accuracy and usefulness of results in the proper context. The public dataset used in this undergraduate research project is the Honda Smart Home. It is a technologically advanced home designed by Honda to pilot new technologies and monitor energy used. Its notable features include battery storage and PV solar panels. They have publicly available data spanning multiple years at a 1-minute sampling rate. During our pre-processing phase, I integrated the time sampling resolution to the 5 and 15-minute mark as well as hourly. The lower resolutions better represent the data collected at the average house by smart meters as of now and historically. The load profiles shown here look very different at different sampling resolutions and would greatly impact the machine learning predictions as peaks and fast variations do not show in hourly data. This is especially relevant with highly variable loads such as HVAC. The HVAC power usage is shown in comparison to the lighting, which is more regular with little influence from human behavior and serves as an initial training dataset for predictions. A long short-term memory or LSTM model was selected based off of previous residential load forecasting papers that predict high-resolution variable loads. An LSTM model is an advanced form of a recurrent neural network that is capable of learning long-term dependencies and patterns. They include a memory input of the previous cell's last state and compare to decide which information to keep or throw away. There are many variations of an LSTM. We used the vanilla model without modification. We built the model in Python using the QRS library for day-ahead predictions. There were 30 epochs with a batch size of 32 for the initial lighting prediction shown here. The model trained with lighting load at the hourly time step so that a prediction for power used by lighting for every hour the next day can be made. This is an initial result that shows suitable correlation with moderate training as the model is able to predict the timing of the peaks in power usage. Farther predictions will be at higher resolutions for better correlation. As machine learning pre-processing requires substantial effort, this project will continue past this conference and additional results will be reported in future papers. A main goal is to identify the minimum set of data to be collected and used for electric load forecasting. Anticipated recommendations will include a best applicable machine learning model to be implemented by utilities for residential load forecasting. In industry, these predictions may be used to schedule ancillary services and use DERs and batteries for the reduction of energy use and pollution. The artificial neural network method, which has been used by power utilities in the past for forecasting of large loads, will be compared to the LSTM model to draw conclusions on the feasibility of big data collections at high resolutions directly at the smart home level.